Good evening, everyone. I'm Anwesha. I'm the Outreach Officer for AstroSoc, and I'm also the Physical Sciences Editor for SATNAV, which is our university's only science magazine and is student-led. Today, I'm going to be talking about the Kessler Syndrome, which I like to call Earth's unwanted cocoon. This talk is part of World Space Week celebrations 2020, and for the first time, University of Birmingham is part of the celebrations due to our four societies collaboration, which is AstroSoc, SATNAV, SpaceSoc, and WISE. So with no further ado, I'll get started, and along the way, I'll be sure to fill you with facts about World Space Week and the impacts of satellites. We're going to get started with discussing what the theme of World Space Week 2020 is. The theme for this year is Satellites Improve Life. And that is true for the bigger picture. Yes, it is. Satellites affect countless aspects of our life. And life as we know it today would not have been the same without satellites. However, along with satellites comes a price to pay. And that price is what I'm going to discuss with this talk on the Kessler Syndrome. So here we go. To start it off on a sort of lighter note, I thought I'd bring up something that maybe some sci-fi enthusiasts might find themselves being familiar with. One of them is the movie Gravity, which quite deeply deals with this aspect of space debris. It touches on a Russian satellite which creates a collision, and eventually there's a cascade of space debris all over, and it's just basically a dramatized version of that, and it did quite well in theaters, and it's quite a nice movie if you want to watch it at some point. The picture on the left that you see is a Japanese animated TV series called Planetes, if I'm not wrong. I could have said that very wrong. Please excuse me if I have pronounced that wrong. And effectively that also deals with the Kessler Syndrome and the idea of having a shell of space debris around the Earth. As with most fiction things, it has been dramatized a fair bit, but it does capture the gist of what the Kessler Syndrome and what the negative impacts of space debris are. So with that in mind, let's try to understand the phenomena that they have explored from a fictional perspective in these two pieces of work. So with the theme being Satellites Improve Life for Space Week 2020, I thought it would be nice to sort of start off by appreciating the use of satellites in our everyday life. For instance, in long-term spaceflight simulations with the International Space Station, in the future, different space agencies around the world, such as NASA, ESA, or JAXA, they are intending to send humans to distant areas of our solar system. I'm not sure if Mars would count as distant, but it is further than the moon, so I'm going to count that as distant. So in order to send humans to Mars, we need to have effective simulation frameworks, and what's better than sending people to live off in space for longer periods of time and sort of, come to grasps with that idea of being away from Earth and doing research in an environment that is not an environment that they're used to. In fact, if you want to know more about what living in space and isolation feels like for astronauts and get a more of a sort of psychological perspective on this, I highly recommend checking out our last talk in the Quarantine Talk series, which was given by Dan Hunt. It was an excellent talk called Earth from Space and had quite an interesting perspective into the life of astronauts. Focusing back to our topic at hand, another thing that we all appreciate satellites for is television and communication. I cannot imagine going a day without WhatsApp, because if I don't have WhatsApp, I cannot talk to my parents who are several thousands of kilometers away from me right now. And yeah, life would be sad without that, wouldn't it? Another one would be climate and environmental monitoring. That's studying our planet's geology and weather evolution and how that affects our day-to-day life. And not just our day-to-day life, but even in the long term. For instance, climate models from satellite data already show that global warming is real. Some other aspects that satellites are quite useful for are navigation, GPS. Thank you, Google Maps. I love you. I would be so lost in my first week on campus if it wasn't for you. Reconnaissance by government agencies, development in all aspects, astronomy research. Gonna give a shout out to our Quarantine Talk series again. Do check out the talk on the Spitzer Space Telescope by Tutku, which was also given as part of Quarantine Talks. And she did an amazing job of talking about the Spitzer Space Telescopes and how Spitzer was used in infrared astronomy. Another thing that satellites are useful for quite a lot is remote sensing and imaging. So now that we grasp how we can appreciate satellites more and how they impact our everyday lives, let's take the not so pleasant road and see what would happen if we focus on perhaps a tiny bit of the negative. But before we do that, I'm going to throw in some numbers just so we get an idea of what is the scale of the matter at hand. In 2018, we launched 114 satellites into space. The next year, we launched 95. Now, space debris is any man-made object in space that is defunct. So, it's useless. It's just a piece of metal flying around in space, not useful for anything except for being a threat to other useful objects. Now, if we take a look at the statistics given by the European Space Agency, also known as ESA, or ESA, as some people prefer to call it, the number of rocket launches we've had since the start of the space age, that's effectively 1957, so that's about the time that we sent the first satellite into space. That's about, if I round it up, 6,000. They're excluding failures, so if I try to include the failures off the top of my head, did not take this as official word, let's say about 6,000 satellite rocket launches have taken place so far. And all of these rocket launches have placed a total of about 10,000, again rounding it up, satellites into Earth orbit. Out of these, about half of them are still in space, and even further than that, only about half of the ones that are still in space are functional. There is a surveillance system called the Space Surveillance Networks, and they have been doing it's quite a tedious job as well for them, of cataloging all this. And they say that we have about 22,000 pieces of space debris. And the estimated number of breakups, explosions, collisions, or any sort of dramatic event which could result in fragmentation is more than 500. And if we could, sort of put all of these space objects together that are orbiting the Earth, that would be more than 8,800 tons. That's a bit too much, don't you think? So the number of debris objects estimated in orbit around the Earth, according to the ESA, 34,000 objects greater than 10 centimeters, 900,000 objects between 1 and 10 centimeters, 128 million objects from greater than 1 millimeter to 1 centimeter. It's like grains of sand scattered around space, but far more dangerous. Now let's switch gears and go to North America for a bit. NASA estimates the following: 500,000 pieces of debris up to 10 centimeters in length, 21,000 longer than 10 centimeters, 100 million shorter than 1 centimeter. Come to think of it, the gist that I would take from this is that it's a lot. The numbers are not small, and it's not something worth ignoring. Now, although I did mention that it's something not worth ignoring, I'm sure you'd want to know, why does this matter a lot more than, just being really big, scary numbers? Short answer, today's talk, Kessler Syndrome. Now, if I was to give a long answer to this for a little bit of, I guess, a drum roll dramatic suspense kind of effect, I'd say all of this that you see up here, technology, communication, data transfer as we know it, say goodbye to it. It would all go away if the Kessler Syndrome came true, which I try to be optimistic about things, and I'm positive we will come to a solution, but from the way things are looking right now, it seems kind of inevitable, but there's a good chance it could be avoided, and we'll get to it in a bit. If I was to represent the Kessler Syndrome in a picture, it would effectively look like this. Now, at first glance, this might look like, maybe someone's painted a circle with some paint splattering here and there, but you can probably see where I'm getting to here. That circle is the Earth, and the splatters that you see, those are satellites orbiting the Earth. And when I was doing my research for this talk, I came across this really useful animation/video by Dr. Stuart Gray, who is a lecturer at UCL, University College of London. And he created this little animation or infographic, as I guess, to show how the amount of space debris around our Earth has increased from the first satellite launches back in the 1950s up until 2015. So let's have a look at this. I hope this works. So you can see that in 1957, 2 innocent little satellites orbiting the Earth. And as the years go by, well, I think you can see it quite for yourself, how dramatic it is. And that's where we are right now. Not a very pleasant picture, if someone asks me. There we go. One of the most significant developments in recent history with regards to space debris was the Fengyun 1C anti-satellite test. Please forgive me if I did not pronounce that right. This one event created over 3,300 trackable objects. The Americans have a system called the U.S. Space Surveillance Network Catalog, and this grew by 25% of its size up until that point. That's how significant this was. This anti-satellite test took place on the 11th of January 2007, and as I mentioned before, it was conducted by China, and it was basically done by intercepting their satellite, so the 1C satellite, with a missile, so a surface-launched medium-range missile, and the collision occurred at about 900 kilometers on a near-polar orbit, and this one collision, 3,300 trackable objects added. Additionally, this actually wasn't the only space collision. I haven't included this on this slide, but it is still kind of interesting to know. In 2009, there was an incident that some of you might have heard of called the Cosmos-Iridium collision. And this was a collision between a Russian and an American communication satellite. And this, in recent history, it brought space debris to the limelight quite a fair bit, because I remember, I think I was probably about 8 or 9 when this incident had happened, and I clearly remember reading a lot of articles, like seeing stuff on newspapers and space.com, and I remember being kind of fascinated by this, and especially I remember YouTube had some fancy videos and animations to show how this collision would have sort of, contributed to the dangers of the space environment. Now, one of the key concepts with regards to space debris and collisions in outer space is the idea of collisional cascading. Collisional cascading starts off with its roots in orbital mechanics, as we can see from this flow diagram. Now, when we mention orbital mechanics, this could do with the inclination of the orbit, how the satellite is oriented, what's its orbit like, is it geostationary, or is it like on a polar orbit? So basically anything to do with how is the satellite moving in space. That's where the roots begin, because the satellite is effectively moving in space. Step 2, we arrive at collision. As we can see, 2 key factors play into this. Orbital inclination, so how is the satellite tilted, if you like to think of it that way. And number 2, collisional velocity. How fast or how slow is that satellite moving? Though eventually, this proceeds on to an increase in subsequent collision rate and number of fragments. So when you have a collision, you end up creating many more smaller fragments, and eventually these fragments can serve as projectiles themselves, and that could eventually lead to a cascade, kind of like a domino effect, if you would like to say, of collisions in outer space. Further down, we can break collisional cascading down into 3 categories. Now, the categories are kind of self-explanatory. There's 3 of them, called the first one being negligible non-catastrophic. So something that scientists can track down and say that, okay, this is probably not harmful enough to damage any significant, pieces of technology out in space, so this is not too much of a concern, which is why it's negligible. The other one is non-catastrophic. This one is maybe a tiny notch worse than negligible non-catastrophic, in the sense that it may not cause any direct damage to any major satellites in space, but it would still contribute quite significantly perhaps to the density of space debris in that region, and perhaps in a long time it might eventually re-enter the Earth, it might not, or there's a very small chance upon tracking that this non-catastrophic collision fragments would actually damage any other useful satellites in space. Now the third one, catastrophic. Catastrophic basically spells disaster. What this means is that the fragments created from such a collision would trigger a chain reaction of even more collisions. So as we saw in the previous slide, it would result in an increase in subsequent collision rate and number of fragments, and the cycle would sort of, multiply over itself. Now I'd actually like to quote Donald J. Kessler, who he's the person that the Kessler Syndrome has been named after. And this is from one of his papers. And this is what he has to say. Both the current population of man-made objects in Earth orbit and objects in the asteroid belt at 2.8 astronomical units from the Sun are in this early collision process and represent an increasing hazard to spacecraft operating in these regions. So we are actually at the start of it. It's not something that we have to look too far into the future for. It's already happening. And I'm kind of sad about that. This picture is a little bit more than whimsical. It might be a little bit dramatic. Yes, Earth doesn't have rings, and I'm pretty sure that the person who designed this picture probably replaced Saturn and just stuck in a picture of Earth in there, but there's a method to the madness, I promise. If the Kessler Syndrome came to be, and if collision cascading got so bad that we have a lot of space debris outside, then the number of small objects, so these small fragments of space debris, would actually be extremely large, and the total area of all the space debris would actually be dominated by this. So the smaller objects would actually dominate the cascading process. And every single collision effectively would reduce the inclination and the eccentricity of the total population of the space debris. Eventually, as the inclination and the eccentricity reduces, what you'd be left with is a disk. And this has been kind of popularized or dramatized, but some people say that you could end up having a ring around the Earth if things got too bad. This useful graph shows the rate of increase of the number of objects in outer space. As we can see, roughly this follows a linear trend, and we can see how as the years go by, the number of objects seems to be steadily rising, except for this sort of massive jump between 2006 and 2010, roughly. You can see that the total number of objects is shown by this line, whereas the fragmentation debris right here, and this is right about the time of the collisions that we discussed earlier, so my guess would be that this would actually have to do with the two collisions, like the Iridium collision and also the Penguin 1C test. Spacecraft, as we can see, don't really contribute as significantly to space debris. It's still higher than the lowest ones, but it's not too bad. Mission-related debris sort of roughly, I would say, has stayed constant, although it seems to have increased very slightly. That's because many times when rockets are launched into space, they often have a form of re-entry, like they burn up in the upper atmosphere as they re-enter, and that doesn't cause too much debris to be left back in space. Similarly with rocket bodies as well. If we take a little more of a scientific turn to this, we can have quite a neat little look at this in the sense that it says that the engineering development should begin now because there is little uncertainty that it will be required. That's what Donald J. Kessler, the founder of the Kessler Syndrome, has to say. And that is quite a grim fact to accept, but engineering is all about ingenuity and coming up with solutions, innovative solutions to seemingly catastrophic problems. If you ask me, I am positive we can come up with a solution to the Kessler Syndrome not to the Kessler Syndrome, but to the space debris crisis, and we are going to discuss that in the next couple of slides. Now, if we take a closer look at this paper, I'm going to slightly diverge from our scientific topic and just maybe focus a little bit more on the logical side. This paper was published in 1991, as you can see with the red circle right there. That's about 20 years ago. Sorry, 30 years ago. So we've known that collisional cascading and space debris is an issue for quite a while. I mean, 30 years? Not a small amount of time, if you ask me. Trust me, this is related to our talk. It's not just Tom and Jerry, but let's try to recall, I guess, the gist of Tom and Jerry. Tom and Jerry, I grew up watching Tom and Jerry. It's my favorite cartoon. I mean, even now, if anyone wants to, make me happy on any random day, just show me Tom and Jerry. I'll be the happiest person in the planet. But the gist of Tom and Jerry is they chase each other. And that's kind of what two satellites are doing in space. Now, these two satellite pictures are not the two satellite pictures of the actual satellites which are chasing each other, but I thought I'd just throw this in there as a random, fun World Space Week fact. There's two satellites in space. They're actually called Tom and Jerry. Their names are actually Tom and actually Jerry. And they have been launched on a mission to basically investigate the Earth's water masses shifting, and they will map their effects on our planet's gravity field, on our planet's gravitational field. And these are US-German satellites, and they have been launched from a Russian city quite a couple of years ago, I believe. And it's kind of nice to see that, there's always a bright side to things if we try to have fun, I guess. So back to the topic at hand. So far, we have seen how the Kessler Syndrome can prove catastrophic and what losses we would suffer from them. But if we take a more practical approach, what we do as scientists, as physicists, and as engineers is to come up with solutions. So people did come up with solutions to this problem. Two main solutions: post-mission disposal and active collision avoidance. The first one, PMD, in a nutshell, basically nudge the satellite out of orbit so it has a re-entry into the Earth's atmosphere and burns up. Oftentimes, if you can actually view these satellites re-entering, and space agencies also generally issue sort of like warnings before they do this sometimes, so some enthusiasts can actually picture this, and I think I have seen a couple by chance, and it has been stunning every time that I think I have seen a satellite re-entry. The other one is active collision avoidance, and this is sending real-time signals to the satellites to nudge it or maneuver it out of its current position to prevent a collision. So this would be, let's say satellite A approaching satellite B. The Earth Control Station observes that, and they send signals to either one or both to sort of, move away from position in the most effective way. In fact, this is a very active field, and at any given time there's countless satellites and space debris that are being monitored to prevent collisions, and that is active collision avoidance. I would highly recommend reading more into it if this is something that you're interested in. Now, one of the key things that struck me when I was doing my research for this is that if space debris is such a large threat to everything in space, we have the International Space Station in space, and there's people in there, and this inevitably means that they are at risk from space debris. Well, the ISS, lucky for all of us, has actually got quite a robust system in place to protect itself from space debris. The outer shield is designed to withstand collisions and shatter debris object. So if anything hits the outside, it's going to break, basically. It's not going to penetrate through, most likely. It'll be shattered. The inner wall, in turn, is built to, absorb the impact of this resultant spray and not be damaged from, the, shattered debris. The space between the walls of the ISS is filled with fabric, which is actually Kevlar, which is also used in bulletproof vests. And this sort of, package of, that's the first word that came to my mind. Forgive me if it sounds, confusing. But yeah, so this sort of package of protection for the ISS is suitable for debris up to 1 centimeter in size. Now, of course, sometimes you could have a larger piece of, space technology flying towards the ISS, and it could be far too big for all of these systems to be useful. And in those situations, ISS has an advanced maneuver performed. Since by 2013, only just over 15 of such maneuvers were performed, and although this might not seem like quite a massive number, if we consider the vastness of outer space and things being in orbit around the Earth, it does seem kind of concerning. The next bit is something that's kind of a personal fascination for me. Now, many of you might actually have seen this picture. It was very heavily popularized a couple of months ago. It's a picture of the Starlink satellites from SpaceX, and Starlink is basically to improve network coverage, internet coverage over lots of different parts of the world. And while it has its advantages, it does have a whole bunch of disadvantages as well. And one of them is, of course, the sort of idea of having night sky pollution. But the other idea, which is the main idea that I'm concerned about, is the idea of space debris. So one evening, I was kind of bored, and I was doing my research for this talk, and I was like, We know that Starlink is going to be a massive satellite constellation of cube satellites, and I was like, let's put some numbers into it. Essentially, there's two scenarios that Elon Musk plans to do. Either he puts 12,000 satellites into orbit, which is his original plan, or he puts 42,000 satellites into orbit, which is what he actually, sort of wants to do, if possible. At the moment, the plan of SpaceX is to send 60 satellites per launch. Now, let's assume that he gets approval for 42,000 satellites and SpaceX gets up to 5 launches a year. It will take 138 years to put all in orbit. If SpaceX gets 10 launches a year, so that's double the original number I said, it'll have that to 69 years. Now, we all know that Elon Musk is a very smart man. I really appreciate his intelligence. And he would probably want to fit more satellites in a rocket launch. If the plan with 42,000 satellites gets approval, and he decides to launch them all over 20 years, that would amount to 210 satellites per launch, given that there are 10 launches per year. Now, if we go back to the first scenario with 12,000 satellites total and just 10 launches a year, he can get this whole job done in 10 years if he launches 120 satellites per launch, which is just double the current amount per launch. And pretty sure SpaceX and Starlink's engineering team can probably come up with an ingenious solution to send 120 instead of 60 satellites into space. I'm a bit concerned, I'll be honest, because as much as I'd want, all the remote locations on Earth to have better connectivity, I really wish there was more information out there to know what plans Starlink or SpaceX has to, reduce the impact of space debris, because we're talking 40,000 Cubesats. That's going to add a lot of objects to track. Now, as we come to a close for this talk, I thought I would probably leave some of the more enthusiastic members of audience with something that they could probably go on to do further in the future if they're interested in it. And the 8th European Conference on Space Debris, which is run by the European Space Agency, is coming up. And you can see the link here. I'll also try to post the link in the description or in the chat, most likely, if you're interested. And in this image, you can only see 3 of the topics. There's like about 10 topics, if I'm not wrong, from when I last saw the website. And it's all sorts of, debris analysis and how you can monitor space debris and all the nitty-gritty details of what goes into modeling maybe collision cascading, or how the Kessler Syndrome might unfurl in the future. COVID has had some advantages in the sense that we don't have to worry about traveling to places in person, so everything can sort of come to our screens in front of us. So this conference is also going to be online, as you can see in here, and it's going to be in April 2021, so we've got some time, like about 6 months to it, but it's definitely something worth considering attending if you're interested in the field. And yeah, if you have any questions, I'm more than happy to answer it. And with that, I will come to my concluding notes. So if I was to give 3 sort of, takeaways from my talk, it would be satellites are useful as long as they don't destroy each other. Number 2, Kessler Syndrome is inevitable. We have already started seeing the first stages of the crisis, and it's time to take action. Number 3, we have done enough harm to our planet, to be honest. Global warming will be irreversible very soon. And at the least, we could let our space, like outer space, be unpolluted. And I feel like as responsible citizens, it's sort of our job to increase awareness on all of these pressing issues, because it's not just about our generation, is it? It's all about the future generations to come in. Do we want our children to grow up in a world way worse than ours? Probably not. With that being said, the last point that I'll come to is the recommended readings. This was something I found really, really useful. It's a really nice document, paper, and a lot of the information that I just provided to you does come from this paper by Donald J. Kessler. And the European Space Agency has also collected a nice little list of FAQs with regards to space debris, and they have nice statistics in there as well, so do give it a read if you're interested in this topic more. And that brings me to a close. Thank you very much for sticking around till the end, and I'm happy to answer any questions you have. Unfortunately, this is not a live talk. This is a pre-recorded talk as it is term time, and if this talk has gone live at 6 p.m., chances are I am walking home right now from campus because I just finished my classes. But do send me an email. I will be sure to leave my email address in the comments or in the description, or just send an email to AstroSoc's email address, which is astrosoc@guild.bham.ac.uk, and I will be happy to answer any questions you have or just to do any outreach work for science. I love science outreach. With that being said, good evening, everyone, and I look forward to seeing you at the remainder of our World Space Week events. Happy World Space Week, everyone!